All right, folks, second video of the unit, 2.1b. This is center of mass problems, and I'm going to go through one that you can solve without any math, and then a couple that you would need some math for. This also is a video where you should have a packet of pre-made notes sheets from me, and so if you wanted to use those now, you can, just because I've written out all the problems and drawn the pictures. So we're looking for center of mass, and so that's what we're going to do. First one says, estimate the center of mass for the following uniform piece of wire. So this is like, I don't know, maybe not an obvious question to answer. But this black line that I've drawn is a wire. Maybe you can imagine like you've taken apart a paperclip and you've turned it into a rectangle, but the rectangle doesn't finish, where there's this empty space in here. And so that's what we're going to do. So estimate the center of mass for the following uniform piece of wire. Here's what I want to show you. So this wire has some symmetry. If I drew a line here, that's the middle of the object. There's some symmetry going on there. And then if I drew this line, I did not do this perfectly. So I am going to like convince you that I've done this right. I'm just going to forget that little nub of line there. There's a lot of symmetry to this, but there's some missing symmetry, right? Like these two pieces of wire on the left and the right are identical, and so they contribute the same to the center of mass. The top and the bottom, however, are not identical. There's this missing piece. So what I want you to imagine before we estimate is that this was a complete square, that there actually was a piece of wire that connected, and so every side was accounted for. That would put the center of mass right in the middle of the object, right? So there would be symmetry everywhere, but there's not. There is a piece missing here. And the way that center of mass works is it's always closest to where most of the mass is. So if I had a perfectly symmetrical square of wire, and I took away this piece, the center of mass would move away from it. Well, this piece that's missing is on the right side and on the top. So the center of mass would be down a little bit, and it would be to the left a little bit. It would have been pushed away from the center, away from where all that mass is. So I actually can, but I'm not going to determine exactly where this is, like what coordinate it's at. But it's going to be in that like lower left quadrant of space there, because there's mass that's missing from this square. And so more than half of the mass is in this lower section. All right, next one is with math. Find the horizontal point for the center of mass for the three masses connected to a massless rod. These are positioned maybe meters, 0, 1, 2, 3, 4, and so these masses are all connected to one little like piece there, and they're at different spots. So let's calculate. So the horizontal coordinate for the center of mass. There are three objects. So I have to have three terms. And I tried to keep the numbers simple. So we can do a lot of this in our head if we want to. All right, so that's what the equation would look like for the three objects. And now I just need to plug things in. So however many objects, that's however many terms I have, and that's it. So M1 is 1 kilogram, and it's at a position of 0. So in my coordinate system, it looks like that's going to cancel. And all that really does is it reduces the value of the numerator. So it actually pulls the center of mass to the left. The second object has a mass of 2, and it's at a position of 1. The third object has a mass of 3, and it's at a position of 4. That's the numerator. The denominator is going to be the masses all added up, 1 plus 2 plus 3. So the x-coordinate of the center of mass, well, that's 0, that's 2, that's 12, this is 14, and 1 plus 2 plus 3 is 6. And so this is about 2 1/3, so 2.3 meters is the x-coordinate of the center of mass of that object. Okay, and so if you want to put it there, that means it's about there. And it is. It's like closer to M3 because that is the largest mass, and also this mass is a little bit closer to the center than M1, and so that also pulls the center of mass to the right. Okay. This last one is like the one that would be the most difficult out of the three, and it says find the XCM and YCM for the following uniform piece of wire. So this wire is arranged in a U shape, and we are still going to use symmetry to do some of the work for us. So I'm going to draw a line right here. And on either side of that line, there is symmetry. So I know the x coordinate for the center of mass without even doing anything. And again, that's just because the left and right side of this wire are the same. I was a little bit off, but you understand. XCM equals 1 meter. So the horizontal coordinate for the center of mass is along this line because the left and right halves of this wire are symmetrical. And I know this because of symmetry. Okay, so that's awesome. The y component is going to be a little bit trickier. And you'll notice that I didn't give you the mass of anything. This word uniform is really important. It really means uniform density. And that just means that like every segment of this wire has the same mass. So what I would like to do is, instead of imagining this as one wire, I want to imagine it as 3 pieces of wire. The wire on the left has a center of mass that's at 1 meter up. It's this length of wire, if I ignore the rest of the object, and the middle of it is right there. Because any lengthy object that's uniform has its center of mass in the middle. Well, that means that this bottom piece has a center of mass that's at 1 to the right, and this right piece of wire has a center of mass that's also 1 up, same as the other one. So instead of this like long object that has many, many particles, I can break it into 3 pieces where each piece's center of mass is in the middle. Now I can treat that as 3 pieces of equal mass. So I go through my y coordinate equation. So I'm going to write this out just because I haven't written this out before. We are used to this from projectiles, that if it's x or y, you just change the x or the y, and all the equations are the same. And then to find this, I just need to like get the coordinates right. So these are the y positions, so these are the vertical coordinates. So this first one I'm going to have be m1. So let's just say it has a mass of 1. They all have the same mass, so why can't they have a mass of 1? The y coordinate is 1. Let's have this be m2. It has a mass of 1, and its y coordinate is 0. And then this one is m3. It has a mass of 1 and a y coordinate of 1 also. Each thing has a mass of 1, and so that's a total of 3. This fraction works out to 2 over 3 meters, 0.6 repeating. So that is the y location of the center of mass. And if I use the scale that's here, that means that the center of mass is approximately there. So that is the center of mass for the entire object. I already knew the x component, or the x location point, was along here at 1, and now I know that it's also 2/3 up. All right, so that does it for center of mass. You don't have to do a ton of center of mass calculations in AP Physics 1, but it is a concept that was just added to the course this year.